Record. Okay, now I'm recording. Perfect. So welcome. Today, I think it's good that we divide the lecture in two parts. The first part, I continue on the polymers. There were some doubts that some people was asking some questions. And this will be the first part. The second part, I'll start doing the corrections of the exercises. Okay. So first of all, this will be lecture, I think, 19, if I'm not wrong. And we will be biopolymers too. Excuse me if I'm a bit biopolymers too. If I'm a bit slow, but it's been a while. So now, there was a question from the previous lecture about when I wrote this one, E phi in the previous model equals 1 over 2 pi. This was the question by Dionesa, right? So this is a very simple thing because this is the uniform distribution in the interval 0 to pi, okay? It is uniform, it is in all places, is equal to 1 over 2 pi. Okay, 1 over 2 pi. This means that in the model I was explaining to you, what I was telling you is that the angle, so from the first angle that you draw, this is length A, this can take any value. This is the angle phi. So you can put this line here, but you can also put it here. You can put it here, all with equal probability, okay? That's why I put 1 over 2 pi. Typically, when you discuss uniform distributions, you say the uniform distribution in 0L, for example, this is a distribution that takes the same value between 0 and L. It's like this. And then the probability, if X comes from the uniform distribution 0L, the probability of X is 1 over L. Okay. So I'm saying phi is a continuous variable. It has no preferred angle, and all the angles are equally likely. This is what I'm saying. Okay. This will be uniform distribution in 0L, but this is the uniform distribution in 0 to pi, which is the same thing, basically, but L equals to pi. Okay. Does it make sense, huh? Okay. Just this was just a reminder from the previous lecture. So now I will do a brief reminder on statistical physics, which I think it will be useful for what I'm going to explain today. So let me call this part review of basics of statistical mechanics. Of course, statistical mechanics is a big field, so I cannot review all the field. I would need an entire course, but in particular, I will discuss the canonical ensemble. Okay, why the canonical ensemble is because in biology, usually we are in a homogeneous temperature. So we have the cell here. The cell is in a thermal bath at temperature T. And within the cell, if you look at a polymer, it is also, we say, this is in an ensemble at temperature T. Okay, so it makes all sense that the elements of statistical mechanics that we need are the canonical ensemble, which is systems that are in a contact with a heat bath. All right, so the basics I will review is the following. I will call N will be the microscopic configuration. This is the same notation I used the other day. Configuration. And I will associate to each microscopic configuration an energy E sub n. All right, this will be the microscopic state energy. Right. We defined, so the probability for the configuration n to happen is given by the Boltzmann distribution, as you know, in the canonical ensemble. Boltzmann distribution to see the configuration P of n. This, you should know all very well. The probability to find a configuration n in a canonical ensemble is e to the minus beta en divided by z. Okay, you should know this by heart. This is very standard in statistical mechanics, right? So this is the configuration of the energy of the configuration n, and this is the partition function, which is the normalization factor, because this should be normalized in a way that I'm writing it like this. So it means the sum over all configurations. The configurations could be continuous. So in the case of the polymers, this n will be the sum over all possibilities of the angles. This should be normalized. So this means that Z goes out of the sum, because this is a number. And then if you sum this n e to the minus beta en, this must be equal to 1. So then you can move Z to the right and get what is the partition function. This is simple. So it will be called the partition function. So someone even realized why the partition function is called Z and not P or F? Or... It's a curiosity, eh? Okay, this is because Boltzmann was Austrian. So then this is the way you say sum in German is a very long word that starts with Z. Okay, it's like sum, right? But okay, so the partition function is Z equals the sum of e to the minus beta en. Okay, so from here you should know that in the canonical ensemble, if you know Z, you know everything. You can derive almost every quantity that is of interest in equilibrium. Okay, in particular, from the partition function, you can get what is called the free energy. Helmholtz free energy, which is F is obtained as minus kBT log of Z. This is natural logarithm. Okay. This is a definition, but it's called free energy. So now it is also important to know that what is the internal energy of the system. The internal energy is often written as U, but this means the average of the energy, where the average is done over all configurations. Here, when we think about polymers, each configuration is one configuration of the polymer. It could be like this, another could be like this, another could be like this, another like that. This is, for example, n equals 1, and this has one energy, E1. This is n equals 2. This has an energy E2, E3, E4. On the other day, the energy was the same for all of them, because I said there are no interactions between the monomers. But I could make a more complicated model in which, for example, each of these has a spring in the middle. So then there will be an energy associated to each angle. If we have time, we will do this model. It's more complicated, but then each of these different configurations, we have a different energy. It's not the same if the springs are together. And okay, so what I'm saying is that the other day I said this length was A, but we can have a model where this can be stretched and expanded. Okay, so that would be a different. Every of these lengths will have a different energy, and everything will be more complicated. Anyway,
I have a question.
Yes.
I saw like many research work in biology. They all talk about free energy. So what kind of information is provided by free energy in biophysics or in biology in general?
Okay, this is important, and let me go to this in a second. Okay.
Okay.
So free energy comes many times in biology, mainly because the free energy, at least the Gibbs free energy is the most important one. The Gibbs free energy is the free energy of the system when you have constant temperature and constant pressure. Okay, so the amount of energy you put when you add one particle to a system, when you have constant temperature and constant pressure, is the Gibbs free energy. And in biology, the most common situation is when you have constant T and constant P. Okay, and in that case, the thermodynamic potential that is minimized. So if you want to find equilibrium in a system which is isothermal and the pressure is constant, imagine the system, you can change different parameters of the system, but the pressure and the temperature is constant. Equilibrium is reached when the Gibbs free energy is minimum. So Gibbs free energy depends on the configuration, but the configuration in which you have minimum free energy is equilibrium in this ensemble. Today I'm not putting the P, I'm doing a simpler ensemble, which is just constant T. But it is simple to go into that. You can go to thermodynamics books and find it. But Gibbs free energy makes sense for this reason. Constant T, constant P, it is the thermodynamic potential that is minimized. Okay, but okay, let me continue and I'll show you something important related to this. We could talk for forever on statistical mechanics. Okay, so what is the internal energy? Is the average of the E. So it is the sum over n of E sub n, P sub n, right? Is the average of E. So you average with the P, E sub n. But what is P sub n? We know it very well because in this ensemble, P sub n is, again, E minus beta, En divided by Z, right? So this will be relatively easy to calculate. And now, let me add another one, which is also useful, which is the entropy. But first of all, there are many entropies, and I do research on that, so I should be precise. This is the system entropy. Okay. We are thinking now, to be precise, of there is a thermal bath with lots of molecules at temperature T, and there is a part that is called the system. It's a small part of the entire universe, okay? So what I write here, this is very important. These are all for the system. Free energy of the system, internal energy of the system, system entropy, entropy of the system. The entropy of the bath is something else. It enters in the second law of thermodynamics, and we could talk a lot about it. But this is the entropy of the system, which is the measure that I talked about to you before, which is minus kb, the average of log of p. Okay, this is the Gibbs-Shannon entropy. So if you see, this is nothing but minus kb, the sum over n of Pn log of Pn. Okay, why I'm doing this? Okay, it's the average of log of P. I put log of P and average with P. Nothing else than that. So now you should realize that the P of n, if we do log of P of n, is log of P of n has two terms. One is log of this. The log of the product is the sum of the logs. So first we do the log of this, so it's minus beta En. Actually, there is a minus here. So let's look at minus log Pn. Is this. And then we have plus log of Z. Okay, you follow me with this, no? So, okay, sorry, if maybe you learned this in your other course. If you did, please tell me to skip.
No, it is plus beta En.
Exactly, plus beta En.
Yes.
Plus beta En, exactly. Yes. All right. So we have beta En plus log of Z. So the first will be, let me take the log of Z here. So minus log of Pn will be log of Z. So if I continue, sorry, I have a space, but there is a problem with this. Okay, that's better. Sorry. So we continue. So now I use this relation. So there will be KB log Z times the sum over n of Pn. And this is equal to 1. Okay, so we have the first term. And the second term will become, there is a beta and Kb. So beta is 1 over Kbt. Remember this. Beta is 1 over Kbt. So beta times Kb is 1 over T. So it becomes, and let me continue, plus 1 over Zt, sorry, I said it in Spanish, 1 over Zt of sum over n e to the n e to the minus beta en. Okay, so you should realize one thing from here, which is the following. It is that if you take the free energy and you take the derivative with respect to t, you will get this result because you do the derivative of f with respect to t. So this depends on t, but also z depends on t because there is the beta. So the first derivative of f with respect to t will be minus kb log of z, which is this, with a minus sign. The second derivative will be basically z prime divided by z. So there will be a z, which is this, and the derivative of z with respect to t will be this. So this means that S is minus partial f with respect to t. So you see what happens, no? That if you get the partition function, from the partition function, you calculate the free energy very simply, then the entropy is very simple. It's a derivative of this. So if you have this in the canonical ensemble, you know basically everything in equilibrium because the Z appears here. Once you know Z, you know F. Once you know F, you know S. Okay, so you calculate almost everything knowing the partition function. Okay, something else you can check is the following relation. It is that F is U minus T times S. The free energy of a system, it's its energy minus T times its entropy. Okay, and here you see something important as well. That is, in the canonical ensemble, you reach equilibrium when F reaches the minimum. It's something that, okay, I cannot prove it here in a second, but this is important knowledge. F, you minimize it in equilibrium. So it means that in equilibrium, you can reach equilibrium either minimizing entropy or maximizing the entropy. And there is, at a finite temperature T, there is a tug of war between energy and entropy all the time. And this is happening also in biological systems. There is energy, but there is also entropy. When there is a thermal bath, the equilibrium state is the one that makes this minimum. Okay, the one that makes this minimum has the two contributions. I want to be low energy, but I want to be also high entropy. And what is telling me how to gauge the balance is the temperature. Okay, this is something else we can tell you, but I believe with this we can go ahead with the polymers. Okay, so give me a second because I wanted to explain you something else. So I introduced something else which is also useful for the next model that I will explain. So 1 second, let's see if this works. Fine. So now I will explain what is called the force ensemble, which I can, okay, which is the following. So now imagine that you have a system where it has, for example, in the polymer, we will discuss the following system. You have the polymer, it's Okay, the polymer will have a given energy. It could be that there is an energy between its monomer, but then there will be also an external force here. The force will be applied to all of the monomers, okay? So in this situation, we will have what is called the L force ensemble. It will be canonical ensemble, but in this situation. In this situation, what happens is we can think about a modified partition function, which is defined like this. It will be sum over n of E minus beta is a n minus F ln. And ln is the total length of the polymer. So I will define here ln as a sum from I equals 1 to n of cosine phi I. Okay, why I'm writing this? Because cosine phi I is the projection of each monomer in the horizontal. Okay, this will be the total length, which will be this one, the total length along the x-axis. Okay, this will be this. So when we have this, let me tell you something that we can also define a thermodynamic potential. I will call it H, will be analogous to the free energy, which will be minus kBT log of z. So the same story, okay? The same story. And now something one can prove is that if you take the derivative of this H with respect to F, it will be the same thing. It's very easy to do this because if you do the derivative of log of z is the derivative of z divided by z. So it will be minus kBT okay, z bar, and here we put partial z bar with respect to f. Okay, very simple algebra. So if you do this, you get minus kBT. This should be easy for you because in the end, z is a number. It's a number that okay can depend on these quantities. As you see, z here depends on the temperature. You're summing over the end, so it won't depend on the energy at the end. It won't depend on the length at the end. You're summing over these guys. So this will be a function of beta and f in reality. These are the only variables in which z bar depends, okay? So the derivative with respect to f divided by this, it gives you, when you make the derivative with respect to f, it's the derivative of the exponential. So then it will come beta ln down and then this. So there will be a beta and then ln will come down in the derivative. Okay, n will be ln, and there will be e minus beta en minus f ln. Okay, this is what we get. So now you can realize the following. You can realize that, first of all, kBT and beta cancel. Second, I can drag this here. So I take this z and I put it here. Oh, this wasn't good. Oh my God. This is the problem of doing things live. Okay, this was ln e to the minus this, and I dragged here z bar. Okay, you see what happens. You see that now this is the canonical distribution. This is P of n. So this is Pn ln, is the average of L. So what you get when you do these things is, well, there is a minus, if I continue, it's minus the average of L. So the average of L in this ensemble is just, you compute Z, from Z you compute H minus kBT log Z, and then you take a derivative. That's it. This is a good thing of knowing a little bit of statistical mechanics. You know partition function, and then this gives you all the information. So I can get all the configurations. So another configuration would be, I don't know, something like this, no? Like that, the force. Another one will be, I don't know, highly wrapped like this. Okay, like this. Okay, the lengths will be different. Each of them will have a different length. This will be P of L. Okay, I don't know how it will be, something like this. Then I'm looking at the average value. The average value of all these configurations is just you need to know this. That's it. Okay, so similarly, you can show the following, that you can get also the entropy as minus partial H with respect to T. As I did before with the free energy, partial F with respect to T with a minus. Yeah, that's it. The length is just minus this thing, and S is minus partial H with respect to T. So this way, we can write something like this type of relation, dH equals minus S dt minus average of L dF. This is what people like in classical thermodynamics, write it in this way. It means that if you change slightly the force, the change of H will be LdF. You can also get directly from here, but this is also another way of writing this. S is minus partial H with respect to T. Okay, usually in thermodynamics books, they do it like this: partial H with respect to T at F constant. Okay, and the other they write partial H with respect to F at T constant. This is what you find in all classical thermodynamics books. So this is often called the Legendre transformation as well. Legendre transformation, which for this problem is F equals the free energy equals H plus LF. So dF, it will be the real free energy, will be minus S dt plus FD. Okay. But this is not so important. So what I think is key for you is to know these relations that you can use to get the average length, which is what I'm going to use later. Okay. So let me go now to a more precise model. So what I'll do is I'll now discuss the second example, which will be the freely. Okay, so all this I explained, you knew it. Maybe it has been a bit boring, but I just wanted to be sure. Did you hear about that before in your courses? If it's yes, say yes.
Yes.
Okay, fine. But the reminder is good, no, for you?
Yes.
Okay, good. Good to know. Fine. So let me go to this model I'm trying to introduce to you. So you have the polymer with segments of equal length A, and they have different angles. And now they are subject to a force. So the microscopic configuration will be, again, all these angles of the polymer. We say it has n sides, 1 to n. And now we can say what is the length. The length for a configuration n is what I said before, the projection in the x-axis, cos phi I. And from here, we can define the partition function simply, like the sum over n, E minus beta, En minus FLN. Okay, fine. So now let's do something easy. First of all, we know this ln. It is this sum, so it will be this sum inside here. And En, in this case, is simple. This is the general theory that I gave you for any energy of the configuration, but now we have very simple. En is 0. The only energy that comes here is from the force. In the previous example that I discussed, this was 0. And the partition function was very, very simple. Okay. But just, okay, if I remember well, give me a second, because I'm coming back to this case. Actually, there was no partition function until here. At the end, discuss the partition function. Yes, but it's trivial in that case. In this case, there's no energy associated. There's no like springs, for example, or something like this. It's just someone is pulling and is pulling from all the monomers. Okay, so in the end, this is like giving an energy which is minus Fl. Okay, this is what this means. All right. So given this, let's calculate the partition function. Let's do this sum. This means we do this, and we sum over all configurations. This is a sum, but we can do it like this because here the phase space is continuous. There are all these angles, okay? There are all these angles. This is this angle. This is this angle. This is this angle. And this is this angle. So this is the phase space. Then we have to sum like this. D phi 1 to D phi n from 0 to 2 pi. This is the way we sum our configurations in this biopolymer model. Now, what we need to put here is e to the minus beta this, which is e to the minus with minus is plus, so it will be e to the beta f, and ln is a all this sum, a, and then all this sum. Somewhere sorry, some this was not perfect, so we have to take this out and put sum I equals 1 to n. So this is sum over I of cos phi I. Okay, this is the partition function. Formally, this is the partition function. Now I ask you, what can we do with this? Anyone?
Everything. It's the partition function. So whenever
Yeah,
we
sure.
need to
That's
find.
true. Now, fine. Good. You got the first point of the lecture. So now I'm saying I would like to calculate this, get a number, get a, I don't know, is this?
Yeah.
Okay.
The phi are random variables or what?
Yeah, I would like to do this integral. That's what I mean. So is this simple to do, you think?
It is simple because we just expand the sum, which is the product of the exponential, and since they are independent, we can calculate each integral, which would be the same. So it is an integral to the power of n, integral of something to the power of n.
Exactly. This is 0 to 2 pi. We can call this d phi.
Excuse me, Professor. We have your voice very low volume.
Yes, sorry, I was relaxing a bit.
It was going far and far.
Yeah, you see, I cannot relax in a second there with you. Okay, this is 0 to 2 pi of d phi, and then it's e
exponential beta
beta a fa cos phi.
cos to the power of n.
This to the power n because we have n. All right. So now my question is, can we do this integral? Do you know what's the integral of something like this? E to the, let me call it alpha cos phi. Have you seen this integral before?
I guess it would be like 1. Wait a minute.
It's an exponential.
So it is.
It's an exponential. Okay, so this integral.
So it is 1 over alpha sine of theta, 1 over alpha sine of phi, exponential of alpha cosine phi.
No, be careful, because now we are not doing the integral dx e of ex cos beta. This is very simple because I'm integrating in x, and this is like integral of a constant times x. Now, the integral has a different shape. The integral has the shape of e to the k, whatever constant, cos x. Yeah. It's exponential of cosine. This is much more difficult. I can give you the answer. The answer of this is 2 pi, the Bessel function, modified Bessel function of the second kind of order 0 evaluated at alpha. It's a much less common result. This is called Bessel function, this one.
Yeah, and there is a yeah.
It is not so obvious. This one. It is called the Bessel function. So
Yeah, actually, I had a course about Bessel functions before.
okay, that's very good. It is called a special function. So this result here, it's 2 pi, the Bessel function of 0 order evaluated at beta fa. Very important when you see this type of special function, what comes inside should be dimensionless. Okay, we couldn't have a special function of beta because beta has units. But this is beta fa, which is the same as saying fa divided by kBt. So it's an energy divided by an energy. Okay. This is correct. This is fine. This you have to take care always that things make sense in the dimension. Okay, so this is like this. So then we get 2 pi Bessel function evaluated at beta fa to the power n. That's the partition function. Calculated. We can do it, which is good. All right. So now, having said this, we can now, interestingly, calculate the thermodynamic potential that I call H. They said H was just minus this kind of a generalized free energy minus kBt log z. And log z is trivial because it's a log of something to power n. So it's n log this. So this is just minus n kBt log of 2 pi H0 beta fa. That's the free energy. From this, as I was teaching to you minutes ago, we can get the average length in this model, and the average length is minus partial h with respect to f, and h is given by this. So partial h with respect to f, the only place where f appears is here. So it will be, is a partial derivative of a logarithm. So with the derivative of this divided by the logarithm. Sorry, the derivative of this divided by this. So in the end, what comes out is the following, with a minus. The minus kills this minus. This n kBt. There will be 2 pi and 2 pi which cancel. So there will be in the denominator I0 of beta fa. And in the numerator is the derivative of I0 beta fa. Okay, this is the derivative with respect to f. Okay, so if you make this derivative, what comes out, and now let me tell you something, is that this is a property of the Bessel function, is that if you take the derivative of I0, let me call this I0x. So here I'm putting, just for completeness, the Bessel function is, if you write it as a function of a variable x, it is defined like this. Okay. So you are integrating, you are not integrating over x, remember, you are integrating over phi. The first derivative of the Bessel function is the Bessel function of order 1 at x. It's another Bessel function. Now we are taking the derivative with respect to f, so there is the beta a that come out, beta cancelled with kBt, so it's Na I1 beta fa divided by I0 of beta fa. And this is a nice result because we get the average length of the polymer in terms of the different parameters of the system. So this will be the average length calculated over all possible configurations of the polymer. Now, let me copy the result. So I said average L is Na I1 beta fa divided by I0 beta.
Excuse me, Professor, you moved to the new page. We lost everything.
Oh, Okay.
Sorry.
If you want, we can do a short break. If you need a break.
No, but I think cleaning the board from the bow and continuing in this way will be okay. Because when you move to the next page, we are just writing and we lose everything.
Let me know. Let me know. Just tell me when you are done with this copying.
Thank you. Yes. Okay, for me, it's done. Thank you.
The rest are fine.
Yes.
Okay. Very good. So this is the result, and now let me just okay, the Bessel function may be a new friend for you, so it's good to know something about them. So I won't explain much, but just the basics. So these are called the Bessel function. Actually, the modified Bessel function of the first kind. I believe it's the first kind. Maybe I'm making a mistake here. But these are called I's. There's also the J Bessel functions. So these functions are as follows. So function I0. Okay, this is x, and I'm going to n0. And I define Bessel function as this, as 1 over 2 pi. Okay, I have to go back. It's 1 over 2 pi, integral of 0 to 2 pi, of d phi, or I can call this dy if I want, into the x cos phi. Okay, this integral, so x is the variable that remains. So x, this is the first one. This is called I0. At x0, it takes the value 1 here, and then it grows. Then the function I1 is like this. This is I1 of x. It starts from 0. And the function I2, it goes below. So all the others, they are monotonously increasing. All the rest are below. So there is an order relation. Then there will be I3 like this, okay? And so on. They are positive. So an important result, so as I said, is I0 at 0 equals 1, and I0, sorry, I lost it. I1 at 0 is 0. So if I take this to 0, this will be 0, because I0 at 0 is 1 and the other is 0. Okay. It's also useful to know asymptotic expansions. Asymptotic expansions or limits of these functions. So when x is smaller, much smaller than 1, we get, by the way, this function can be defined also with complex argument, but here I'm just showing when x is real. So it's one piece of the cake only. Okay, this is 1 divided by gamma. This is the gamma function, alpha plus 1. And this is x halves to the power alpha. So this means when alpha is 0, this goes flat. So the slope is 0 here. But when alpha is 1, this is linear. When alpha is 2, this is quadratic. That's why we have this story. Okay, and when x is large, what we have is that I alpha goes like e to the x divided by square root of 2 pi x. This means they converge together. I mean, this will be together along alpha because there's no alpha dependency here. If you go to Wikipedia, you can check. There are other corrections. I don't know. I think it's 1 over alpha x 1/3 or something like this. Later, alpha appears later in the series, but the first term it's independent of alpha. This is important. Okay. So now, given this, what we can do here from this formula is take the limits. So if I take the limit when f is 0, it's like taking the limit x to 0. I1 at 0 goes like x, and this is independent. So this L will go like, when f is small, there will be beta f a to the power 1, and then something, whatever is a constant, so it will be something proportional to this. So when f is small, this will go to 0. When f is small, f small means f smaller than kBt divided by a. This is important. When you get this in mathematics, it's not the same as you do it in physics. In physics, things are dimensions. So you see x here is beta fa. So if this is small, means this is smaller than inverse beta divided by a. Very simple. So it goes to 0 for f small. And when f is large, this goes like e to the x, 2 pi x. It will be e to the this. It will be the same dependency for both. The ratio between these two is 1 at long values of x. So this will go to Na when f is much greater than kBt over a. So, and then you can plot. You can also do the plot of this with Mathematica, with MATLAB, whatever. So in the end, you can get the following figure. This will be beta Fa, and this will be average L of the polymer. So what you get is a dependency, which will be, okay, let me draw like this. Dependency of L with A will be expected something like this. Okay, this will saturate. So it will saturate to a value which is Na. So it starts from 0 for F0, and then it will saturate to Na. Na is when you have all the polymer. It's very, very strong force. So you will have all the polymer in a line. The force is so strong that it's totally stiff in a line like this, okay? The force is very, very, very strong here. So the average L is L, so it's Na. This is 1, this is A, this is 2A, this is 3A, up to Na here. When the force is 0, on average is 0 because, okay, I didn't tell you, this is not a hard wall, so the polymer can also do like this, okay? The polymer can be like this, polymer can be like this, polymer. So in the end, it gives 0 because there's no force, so it's like the random walk model that I discussed in the first day, okay? This limit is a freely joint chain model that I discussed on the previous lecture. Okay. So this is this point. But now we get a more rich phenomenology because of the fact that there is a force. All right. So and the last part of this on this model, I will do one more calculation, which will be about the fluctuations. So up to now, I'm showing you what is the average L, but it is important, as I said to you, to understand the fluctuations. So I'll get now into understanding on investigating the fluctuations. Fluctuations that I would like to understand is L squared. What is this? Right, I know what is average L, but now I would like to know the variance, so the second moment. Okay, very good. So we know, as I explained to you before, what is said. We know what is H, and we know that average L is minus partial H with respect to F. Okay, this was in the previous part of the lecture. Now, what I'd like to do now, okay, so just remember that this that I was getting is that partial H with respect to F is average L, and average L is nothing but 1 over set the sum ln e to the minus beta en minus f ln. Okay, fine. So this set, if you put it here, is the canonical P with ln, nothing else. Now, let me just show you that if I take another derivative with respect to f, what you get is something like as follows. So remember, here there are two things that depend on f. So first of all, what is this? Spotlight? Let me see. Ah, spotlight, nice. Okay, there are two things that depend on f. This here, but just the partition function depends on f. Remember, this depends on f and on t. So when I take the derivative, I have to take the derivative first of this, then keep this like this, then keep this, and take the derivative of this one. Okay, very simple. So there are two terms. First, the derivative of 1 over z with respect to f is 1 over z squared. And then I need to do partial derivative of z with respect to f. And this is again, I get is the following. So I get again, because this is z. So if I make a derivative of z with respect to f, the ln will come. So remember, z bar was sum over n of e minus beta en minus f ln. So if I make a derivative with respect to f, partial f of z, this will come down. So it will be a beta sum ln and the same exponential. It will be the same thing as I have here. So it will be, that I will get is this minus beta en minus f ln to the power 2. This is the first part. And the second part, so I took the derivative of this and I kept this normal. And the second part of the derivative is keeping this and take the derivative of this with respect to f. The derivative of this with respect to f of all this is bringing another ln here and with a minus. Minus with minus is plus. So what you get is, okay, here there's a mistake. No, the minus is plus, with a minus is minus. So I get another minus beta. Sorry, I forgot here beta, because beta comes out once only in the derivative of z with respect to f. There's another beta here, and what enters is sum over n of ln squared e to the minus beta en minus f ln. That's it. Okay. So all in all, what I have is a beta that comes out, minus beta, and the rest, I get this one. Yeah, actually, I forgot one thing. So let me undo. Okay, this is a nice thing of being here instead of in the blackboard. So I forgot that I had a 1 over z as a prefactor, so there should be a 1 over z here. So now if I group this with this is P of n. So this is, altogether is the average of L squared. So minus beta, and this is the average of L squared, this term. And this one is beta average of, okay, I can take this inside. So now I can take this z bar and put it inside. So I can put this here. And this again is P of n. So this is the average of L to the power 2. Average of L to the power 2. So this is very nice because you see from this formula that the fluctuations of L, the variance, L squared minus average of L to the power 2 is minus KBT, second derivative of H with respect to F2. Okay, this is an important relation. This is bad. Let me do something better. which is this. Okay. So this is very nice, and something we have derived simply is often called Kubo Relation. This is okay. The variance of L is related by via the thermal energy to the second derivative of H with respect to F. All right. So now we know what is the derivative of H with respect to F because we calculated for this. So we know that minus the derivative of H with respect to F, which is average L, we calculated in the previous part, and it was Na I1 beta Fa divided by I0 beta Fa. Okay. So now I would like to know the second derivative. So the second derivative is taking one derivative of this because we have already done one. So minus second derivative of H with respect to the square equals. So I take the derivative. First of all, it will be every time I take a derivative, this is I have to take one derivative of this with respect to F. Every time I take the derivative with respect to F, there will be a beta A coming out. Beta A will be A divided by KBT. So I take my internet connection is unstable. It's telling me. So maybe Bora, it's been a bit wild in this area, and there's a problem with antennas. But if you hear me, I continue. Okay, this is the first part. So we took out the derivative in the inner part, and now we have to take the derivative. We need to know what is the dx of I1x divided by I0x. And this I can tell you it's simple because this is I0 squared, and then there's the derivative of this one. So this would be IC. This, remember, is I0 prime. So the derivative of this would be I0 prime prime times this without derivative minus the derivative of this times this. So it would be I0 prime squared. This is what we get. So we get I0 prime prime beta Fa, I0 beta Fa minus I0 prime beta Fa divided by I0 beta Fa squared. Okay, let me just do like this so it's clear. So now we have the variance. This gives us the variance of the length of the polymer. So something I'd like to do before finishing is what is the limit when F is small. So when F is small, okay, limit of F, the limit of.
I guess we have minus A prime 0 square, not only A prime 0.
Sorry, repeat.
In the derivative, we have minus A prime 0 square. I guess, I'm not sure.
Yeah. There was a mistake. Okay. This was a mistake. It is minus I prime 0 square.
Yes.
Exactly. Yes, perfect. So now, something you should know is that I0, when you do Taylor expansion, this is 1 minus x squared over 4 when x is small. Okay, you get this. So now you see that if I do f small, there will be second derivative here. Second derivative of this will be minus 1/2. I take one derivative, is minus x halves, and the second derivative is minus 1/2. So this will be minus 1/2. This one, when f beta Fa is small, it will be 1. This one is x. The first derivative is x. So this one goes to 0. And this one will be the same as this. It will be 1. So when beta Fa is small, the only thing that will contribute is this part. So it implies, you can see that I0 prime prime, I0 minus I0 prime squared in this limit divided by I0 squared is, in this limit, it is I0 prime prime divided by I0, which goes like, this goes like 1, this goes like -1/2. Okay, so all this, when beta FA is small, we go to -1/2 when beta FA is smaller than 1. Right? All this, I repeat, you get it from this part, okay? From the fact that the Taylor expansion is like this. When beta FA is small, you have to develop this near 0, and you get -1/2 of this. There's a minus here, there's a minus here, and I repeat, this is the variance. So grouping all together, we get that L squared minus L squared equals, in this limit, so I will write it as a similar equal, is Na squared divided by 2. Okay, this is also an interesting formula. So the variance goes like 8 squared. This is, you see, it's a different mode than one we discussed the other day, but the phenomenology is not that different, because before we had average L was 0 in the other model. So this is the freely joint chain with force for FA smaller than KBT. This is what we get for the length. And the other day we had no force. So I would expect we get something similar. And we did, because on the other day we said the freely joined, we were having that delta R, which is kind of the length. It was 0. Here it is not 0, but in this limit of F small, it is 0. And the variance, okay, this is the variance of L, was something similar, so it was Na squared. Okay, but this was a different mode. This was the freely joint chain. Okay, this is what we got. Now, 1 second. Now, we just finished by saying the following, that if you have a polymer, and this happens a lot because there are many polymers that behave like springs. So I'm doing a very simple model in which you have the polymer like this, you have a force, and okay, I'm getting this variance. But often in biology, polymers behave like springs. Like springs. Springs, I mean that this happens when the force that you put on them is not very large. So you can do an analogy of this like a spring, okay? A spring that has a stiffness kappa, and therefore its energy will be like something like this: 1/2 kappa L minus L0 squared. Okay, this is a very phenomenological description. We are doing something more precise than that. Okay, L0, remember, L0 is the length, the average length, when the force is 0. This is my definition, okay? So when you have something like this, you realize that here you can do the following. You can do that L squared minus L to the power 2 is the same as saying the average of L minus average L to the power 2. And we said this must be minus KBT, second derivative of H with respect to F squared. Okay. We said that when F is closer to 0, it's close to 0, the variance L squared minus the average L to the power 2 is okay. So something you can get out of this model is that you can use what is called equipartition theorem. Equipartition theorem says that the average energy per degree of freedom, now the degree of freedom will be L, is KBT divided by the number of degrees of freedom. So here will be KBT divided by 2. This is called equipartition theorem, which is valid close to equilibrium. So in this region, okay. So equipartition theorem tells us the average of this is KBT over 2. Okay, so this means on one side we have that this, okay, and this will be kappa halves of a second, kappa halves of L minus L 0 squared. Okay, so actually I think I made a mistake here. I have to correct in my notes. Okay, what I want to say is that L squared minus L average square, from here you get that is KBT over kappa, and from our theory we said that this is NA squared divided by 2. So this implies that one can relate the stiffness of a polymer in this kind of average or coarse grain description, because we know the polymer has more details. It's not just a spring, it's much more complicated than that. But when you approximate it as a spring, then you can say, what is the origin of this stiffness of this spring? What is the origin of the spring constant? You can get it from this equation. In this equation, you get that the spring constant is KBT, okay, actually, yes, it's KBT divided by NA squared. Okay, so there is a relation. This is one of the goals of statistical mechanics, relate macroscopic, this is a macroscopic parameter, with the microscopic temperature, Boltzmann constant, number of monomers, and A, okay, microscopic. So this is just to tell you that when you do a more coarse-grained description of your model, you get stiffness. You can say, okay, my energy is parabolic, so it's I have a spring. Then this spring constant, you can relate it to the parameters of the system when you are able to do this calculation. So here it has been very important that we have been able to calculate things. Okay, so this is the power of using in biophysics models that you can solve. It is very good because you can complicate the models, but then when you complicate it too much, you cannot do these calculations. So when you go to an experiment, you cannot infer properties of the process so easily. Like if you have a model that is simple, okay, this will be the coarse-grained model, and this will be the more microscopic model. This is very, very useful because if you use models that you can solve, then you can do this type of connections. You can say, okay, I can now infer if I do an experiment and I take a polymer and I pull it, there will be force applied to the polymer, and this will be the length of the polymer, and this will do like, I don't know, this experimental data like this. This means this is like a spring, but this means it comes from something like this. And from this equation, you can infer how many monomers has a polymer, which is something very challenging unless you have a good microscope. So just with simple experiments, you can infer these parameters. Or if you know the number of monomers, you can also infer the length of the chain. Okay. I think with this, this is more or less all I want to tell you about this part. I think the next lecture I can discuss with you the solutions to the exercises, or otherwise I can also send it to you so we can discuss. So please, by now, ask me if you have any questions about this part. Is it clear? Could you follow with this whiteboard?
Yes.
Okay, that's good. Okay, let me stop sharing for a second.